All right, this is AP/BC Calculus. This is a BC only topic, so if you're in AP/AB, please skip to the next section, which would be 0706. So we are in Unit 7, Section 5, which is Euler's method. So this name right here is Euler. Please don't say Euler, it sounds awful. So let's talk about what Euler's method is. Euler's method allows us to use tangent lines to approximate the solution to a differential equation. It can be used on any differential equation, but it is particularly helpful to solve differential equations to approximate differential equations that we are unable to solve, right? So here's sort of a visual of Euler's method. The blue is the actual curve, and the red are sort of tangent line segments that are used to approximate the curve. So basically what happens is we start at a point on the curve, we find the tangent line approximation, and we follow it to a certain distance. At that new point, we find the next tangent line approximation that would match the curve, and we follow that to another new point. At the new point, we find a tangent line approximation that would match the curve, follow it to a new point, and we keep repeating that until we get to our approximate answer. So this is our estimate, and here would be the actual value of the curve. So I wanted to throw in here that Euler's method gets a shout out in the really epic, totally awesome movie Hidden Figures. Sort of at an important key moment in the film when they're trying to talk about how a capsule would transition from an elliptical orbit, right, the elliptical orbit that it's going around the planet, right, there's our planet, to switch from an elliptical orbit to a parabolic orbit to land back on the planet, right? So we have an elliptical orbit, an ellipse, and then we switch to a parabola as the capsule leaves its orbit and enters gravity, right? And they're talking about how it's impossible to do the math to navigate switching from an elliptical orbit to a parabolic orbit, and they realize that they can use Euler's method. You can kind of see that in this screenshot that I took from the from the video. So again, Euler's method gets a shout out in Hidden Figures, and it's a great way to solve seemingly unsolvable problems with an approximate solution, right? You can't actually find the real solution, but you can find an approximate value, and that's exactly what they did. So let's go ahead and talk a little bit about Algebra 2 and Pre-Calc. So recall from Algebra 2 and Pre-Calc that the easiest and most useful form of linear equations is often point-slope, right? So here's point-slope form where we have slope m, right, and point x1 comma y1. So x naught comma y naught, my bad. So y minus y naught equals mx minus x naught, right? So if we solve this, right, for y, we'd add the y naught over, and we'd get y equals y naught plus m times x minus x naught. So Euler's method is basically this exact formula applied multiple times. So x minus x naught can be written as change in x, or delta x, which is the step size that'll be provided in the problem, right? It's the distance between one x and the next x, right? So if we go back here for a sec, right, here's an x value, here's the next x value, this would be my change in x, right? It would be x minus the x value would be change in x. The m is dy dx, right? We've talked about that before, where we have slope is the same as change in y over change in x, but evaluated at a specific x and y. And y naught will be the old y value from the previous step, right? So y naught would be the y value. So here, right, the y value here would be the y naught when I calculate this one. And when I go to calculate this one, the y naught would be this new y value that is the old y value to find a new y value. So we're going to go ahead and walk through how to do Euler's method. So there are many ways to write the Euler's method sort of algorithm. The way I write mine is a table. You certainly don't have to write mine the way that I do. You can write this however you want. I prefer my method because it keeps things organized. So basically, you're going to be given some equation for dy dx. You're going to be given some starting point, x and y. And then you're going to be given either a step size, like a delta x, right? So step size meaning delta x, and a number of steps, like use delta x is 0.5 and do it 5 times or 3 times. Or you're going to be given a final x value and how many steps you're supposed to take. I use a table where I list the x and y, the slope, which is dy dx, and then my point slope equation. So we're going to walk through how this works. And again, you don't have to use the exact method I use in terms of how to organize it. Euler's method is a specific method, and you're going to use that, but you don't have to use this table if you don't like it. So example 1, we're given the differential equation 1 over x plus 2 equals dy dx, and we're given that y of 0 is 1. We're going to find an approximate value for y of 1 using Euler's method with 2 steps of 0.5. So we're starting at 0, 1. So 0, 1 is my start value. So I'm going to go ahead and put that in the table. That's where I start. I'm told that the step sizes are 0.5. So the next x should be 0.5, and then the final x should be 1, right? There's my 2 steps of 0.5, and that'll allow me to approximate y of 1. So this value is going to be my y of 1 approximation, right? That's because this is y of 0, and this is y of 0.5 approximately, and this is y of 1 approximately. So I'm going to go ahead and find the slope. M is dy dx. Well, my dy dx is 1 over x plus 2. So this is going to be, my slope is going to be 1 over x plus 2, which is a 1/2. So my new y is going to be the old y, which is 1, plus a 1/2 times the step size, right? Well, that's a 1 plus 1/2 times a half is a fourth, so it's a 1 1/4 or 5/4, right? Now you can either leave that as a fraction or you can make it a decimal. It doesn't really matter to me. Okay, so I get 5/4. So now I have this new point, and I'm going to go through the same process. I'm going to find a slope at that new point. Well, this is 1 over x plus 2, right? So that's a 1 over a 2.5, or a 1 over, this is a 5/2, right? So 1 over 5/2 would be a 2/5. Again, you can write it as a decimal if you like that better. It's up to you. If you wanted to write this as a 1.25, you certainly could, right? So my new y is going to be the old y, which I get right here, right? So I'm going to go ahead and write 1.25, right? Plus my slope, which was, again, if you want that 2/5, you can either write it as a 2/5 or you can write it as a 0.4. It doesn't matter to me which, right? So 2/5 times a half. Well, half of 2/5 is 1/5. So I get that this is a 1.25 plus a 1/5, which is a 0.2. So I get 1.45, right? And that goes down here in my new y. Well, that's my answer, right? So y of 1 is approximately 1.45. So what I'm doing is I'm using a point and a slope, right, to approximate the next y value. So again, to show you back on this picture, what I've done here, right, is I'm using my initial point, right? I use this initial point I have and the tangent slope to find a new approximate y value. At that y value, I use the new point, x comma y, and the tangent slope at that x value, tangent slope right there, right, to approximate another y value. And then I do the same thing to approximate another y value until I get to the y value that I want. So we're going to keep doing practice of these, but that's the idea, right? So let's go ahead and try one. Here's your P1. dy dx equals x plus y, which for the record is non-separable, so you can't solve this one. We're given that y of 1 is 3, and we're asked to approximate y of 2 in 2 equal steps. So here you weren't given the step size, right? But you're going from 1 to 2 in 2 equal steps. So my step size is going to be 2 minus 1 over those 2 steps, which is 0.5. So I'm starting at 1 comma 3. My step size will be 0.5, so 1.5 and then 2. This is going to be my answer, right? That's the approximation for y of 2. If I can get to that spot on the table, that's going to be my answer. So my slope is x plus y, right? So x plus y. So that's going to be 1 plus 3 or 4. That means that my new y is going to be the old y, which is 3, plus a 4 times a 0.5. Well, that's a 3 plus a 2 or a 5. So my new y value is a 5, right? My slope is x plus y, so that's going to be 6.5, right? My new y is going to be the old y, which is 5, plus this 6.5 times 0.5, right? So half of 6.5, right, is 3.25. So that's a 5 plus a 3.25. So I get 8.25. So y of 2 is approximately an 8.25. Again, you don't have to use the table. Lots of people don't. I just find it's a good way to organize my thoughts. All right, so let f of x be the particular solution to this diffie hue. Again, notice that this is non-separable. I'm going to go ahead and write this here. So I can't solve this. We're given the initial condition that f of 0 is 1. So f of 0 is 1. We're asked to use 2 steps of equal size to get to f of negative 0.6. So to figure out my step size, right, I want to go from, so I want to do the final point, negative 0.6, right, minus the initial x, right, divided by 2, right? So this is my ending value minus my starting value. So I'm going to get a negative 0.3, and that fits if you put this in here, right? First step would get me to negative 0.3. Second step gets me to the negative 0.6, which is what I want, right? So let's start by finding my slope, right? It's x plus 2y. So that's going to be 0 plus 2, which is just 2. So my new y is going to be the old y plus my slope times this negative 0.3, that delta x. So I get 1 minus a 0.6. I think I get a 0.4. So now my new slope, right, is going to be x, which is negative 0.3, plus double of that 0.4, which would be a 0.8, right? So I think I get a 0.5. So my new y is the old y, 0.4, plus the slope, 0.5, times that change in x, which is the negative 0.3. So admittedly, you're going to have to do a little bit of math here. Like, I get that that's not the most fun thing in the world, but we'll survive. So I'm going to have to do half of 0.3, right? Well, half of 3 is 1.5, so half of 0.3 is 0.15, right? So I end up getting this as a 0.4 minus a 0.15, and so I end up getting that this is a 0.25. So f of negative 0.6 is approximately a 0.25. Now, one thing to keep in mind on the AP, because I'm sure there's a reasonably high likelihood that somewhere in this video I'm going to add or multiply wrong. Just throwing that out there because I know myself and it's a thing that happens. If you're doing this on an AP and you add wrong, you're going to get credit for doing Euler's in 2 steps, and if somewhere along the way the answer went wrong, you'd lose a point for the answer, but you won't lose the point for doing Euler's correctly. So you want to demonstrate that you understand how Euler's works, and just to be honest with you, it is statistically likely that on a non-calculator section, if 5 of you are doing an Euler's problem, probably 2 of you are going to multiply or add wrong at some point. It's easy to accidentally land at the wrong final answer, but to do most of the steps right and just do something simple along the way. And the College Board knows that, so when they're giving you a score, they're aware of that, and they give you credit for Euler's method in the correct number of steps, even if something went wrong. Obviously, if you're using Euler's method sort of in a hidden figure situation and you were using it to calculate something in an engineering or science scenario, you'd want to double and triple check your work. You'd probably want to be using a calculator. You would want someone else to double and triple check your work. If you were talking about building a bridge and you needed Euler's method for some of the calculations, it would be sort of key that you didn't add or multiply wrong. Anyway, so that's kind of the gist. Let's go ahead and do another one. All right, so let y equals f of x be the particular solution to this diffie-q, right? We're given that f of 2 is 3, so that's going to be my starting point. We're asked to approximate f of 1.8 in 2 steps of equal size. So my change in x is going to be that final x minus the starting x divided by the 2 steps I was told to take. That's going to be a negative 0.1, right? So this is going to be a 1.9. This is going to be a 1.8, right? So my step size is a negative 0.1. And you can just plug that in there if you want, and my dy dx is a 4x minus y. So let's start by finding our slope, right? So my slope is 4x, so the slope here is going to be 8 minus 3, which is a 5. So my new y is going to be the old y, 3, plus a 5 times that negative 0.1. Well, that's a 3 minus a 0.5, which is a 2.5. Right? So my new slope is going to be 4x, right? So 4x is going to be, if this were a 2, it would be an 8, right? So this should be a 7.6. It should be 0.4 shy. So 7.6 minus 2.5, good times, seems to be a 5.1, right? So 5.1. So my new y is going to be a 2.5 plus a 5.1 times this negative 0.1. Now, negative 0.1 is not awful because it just moves the decimal place 1, right? So this is a 2.5 minus a 0.51, right? So I'm pretty sure that we get 1.99, right? And if you need to use a calculator to double check, you certainly can. On an AP, you probably would not have that luxury, but all right. So we get that f of 1.8 is approximately 1.99. All right. So some values of the derivative of f are given in the table below. Use Euler's method with 2 equal intervals to approximate f of 3.4. Okay, so this time I didn't give you the table, right? And I've been giving you the table every other time. It's up to you if you want to use the table. You don't have to. Me personally, I really like using my table. So I'm going to go ahead and use my table. So I have an x and a y. I have my slope, right, which is going to be f prime at that given x value, right? And then I need my new y, which is going to be the old y plus the slope times the change in x, right? So you can see that the change in x, right, because I want two equal intervals to go from 3 to 3.4. So my change in x is going to be 3.4 minus 3 all over 2, which is definitely a 0.2. And that jives with what I can see on here, right? So I have a 3, comma 2. Oh, sorry, it's not 3, comma 2. My bad. Come on, brain, pay attention. The original point is 3, comma 10, right? I want 3.2, and I don't know the y value, and I want 3.4, and I don't know the y value. This is the answer I want, right? This is my f of 3.4 is approximately that value. So if we go ahead and fill out this table, right, I know that the slope is f prime of whatever the x coordinate is, right, which I have in this table right here. So the slope at x is 3 would be f prime of 3, or 2. So my new y value is going to be the old y value, 10, plus a 2 times a 0.2. Well, that's a 0.4, so I think I get 10.4. My slope at the second spot at 3.2 is 0.5, so 0.5, right? And then my new y is going to be the old y, 10.4, plus a 0.5 times that 0.2. Well, half of a 0.2 is a 0.1, so I get 10.4 plus 0.1, which is 10.5. So again, it's the same concept. In fact, if anything, this time I was handed the slopes. I just have to make sure I use the information correctly. Notice that at no point did I need this information, right? I needed everything else that's in this problem, but I did not need that last piece of information. All right, let's go ahead and try one with a table for you, right? So same idea. You don't have to make the table if you don't want. Me personally, I like to make my table. I think it's an easy way to do these problems. So I'm going to go ahead and recognize that in this problem, my slope is just f prime of x, which I'm given in a table. I know that my new y is the old y plus the slope times my delta x, right? So I'm given the starting point of 10 comma negative 4. I'm asked to get to 9.4 in two equal intervals. So 9.4 minus 10 all over 2 gives me a negative 0.6 over 2, or a negative 0.3, which totally jives with the table, right? Because you can see that this is going by negative 0.3. So it's not a surprise here. So this is the answer I'm going to want, right? Let's make this the smaller marker, all right? So I need f prime of 10. Well, f prime of 10 is a 1, right? So my new y, right, my new y is going to be the old y, negative 4, plus my slope, 1 times the negative 0.3. Negative 4 and a negative 0.3 is a negative 4.3. My slope for the next one is going to be the slope at 9.7, which is 10, right? My new y is going to be the old y, which was a negative 4.3, plus the slope, which is 10, times the negative 0.3, right? So that seems to be a negative 4.3 minus a 3, right? Because that's what 10 times 0.3 would be, is a 3. So I think I get a negative 7.3. So my f of 9.4 is approximately negative 7.3. And again, notice, make sure you go out of your way to answer the question, right? Don't just have the table, make sure you go out of your way to very clearly answer the question. All right, so far, in all the previous examples, we've done exactly 2 steps of Euler's method. I would expect that the most that you would ever be required to do by hand on an exam would be 3 steps. So we're going to go ahead and do a problem here, E4 with 3 steps, and you're going to do a P4 with 3 steps, and that's pretty much it. Realistically, you're not going to be asked to go much farther than that. If it's a calculator section, by all means, do not do this adding and multiplying and stuff by yourself in your head. But you're not always going to have a calculator, so we should prepare for that. So let f of x be the particular solution to the given differential equation with initial condition f of 0 is 1. So f of 0 is 1 goes on my table. I know that my slope is x plus y. I am asked to use 3 steps of equal size to approximate f of 1.5. So 1.5 minus 0 over 3 means that my step size is a 0.5, right? So, because 1.5 divided by 3 would be 0.5. So that means that this is going to be 0.5, and then 1, and then 1.5, and not surprisingly, this right here, this is going to be my answer, right? That's what I need. That's my approximate f of 1.5. So let's go ahead and fill out our table, right? So the slope is 0 plus 1, so my slope is 1. My new y is going to be the old y, 1, plus a 1 times a 0.5, right? That's the slope 1 times the 0.5, which is the change in x. So that seems to be a 1.5. Cool. My new slope here is going to be 0.5 plus 1.5, right? So that's going to be a 2. So my new y is going to be the old y, 1.5, plus the slope times the change in x, right? Well, that's a 1.5 plus a 1, so that's a 2.5. My new slope is going to be x plus y, which would be 1 plus 2.5, so that's 3.5. So my new y, and this is going to be the final y that I need, is the old y, 2.5, plus a 3.5 times that change in x, which is 0.5. So 3.5 times 0.5, there's a couple different ways to get here. I don't really care. You can either do 7 halves times 1 half and realize that you're going to get 7 fourths, which is fine, right? Totally cool. So if you do that, that's 1.75, right? Because 8 fourths would be 2. The other way to do it is you can think about it like this is a 35 and you're cutting it in half. Half of 35 is a 17.5, and then you move the decimal place. I don't care how you get there. So either way, I get that this is a 1.75. So that's a 2.5 plus a 1.75. I know it seems silly, but really this is not the time to be embarrassed by adding in columns, right? It's really a shame if you get something wrong because you added wrong. Believe me, I do it pretty regularly. So there's my answer. It's a 4.25. And then I'm going to expressly answer the question and say that, sorry, that's not what I meant. It's not a 1.4. F of 1.5 is approximately a 4.25, right? And we want to make sure that we include that. So we want to expressly answer the question. All right, one last problem. You're going to try 3 rounds of Euler's method, right? So you're given the initial condition f of 2 is 0. And you're going to approximate f of 2.3 in 3 steps. So 2.3 minus 2 in 3 steps is going to be a 0.3 over 3 or a 0.1. So that's your delta x, right? So once you know your delta x is 0.1, you can go ahead and plug that in there. So 2.1, 2.2, and then on my third step, I should land at 2.3, which means that this is my answer, right? So the slope is going to be 2x, which would be 4 plus y, so that's 4 plus 0, so 4. My new y is going to be the old y, 0, plus a 4 times the 0.1, which should just give me a 0.4 rather, right? So 0.4. All right, so my slope is going to be 2x, which would be 4.2. 4.2 plus the 0.4, so I get a 4.6. My new y is going to be the old y, 0.4, plus a 4.6 times 0.1. Well, the nice thing about multiplying by 0.1 is it just moves the decimal place. So this is a 0.4 plus a 0.46. I get 0.86. So 0.86 here, right? So now my slope is going to be 2x, which will be a 4.4, plus the 0.86. So again, this is not the time to be embarrassed about adding straight down in columns. It's actually a really good time to use simple addition skills. So when I add straight down, I carry the 1 and I get a 5.26. This is a 5.26. So my new y is a 0.86 plus a 5.26 times 0.1. So again, the nice thing about timesing by 0.1, right, so is that it just becomes 0.526. So I'm going to get 0.86 plus 0.526, and I'm going to add straight down 6, 8, and when I carry the 1, I get 1.386. So 1.386. And again, this is a level that's a fair expectation for Euler's method, and I'm sure somewhere in this video I've added or multiplied wrong, and that's okay. We'll correct it in the comments. But when that happens, right, even on an AP, you're not losing credit for doing Euler's method that number of times. You're just losing 1 point for adding or multiplying or whatever incorrectly. And that's Euler's method.